Hello, this is the first of the series of lectures dealing with multiple alternatives. In this lecture, we will define some relationships that are possible among alternatives, and we'll do this with some typical examples. Then we will demonstrate with two numerical examples the selection process. In the first numerical example, we'll apply present worth for independent alternatives, and in the second one, rate of return for mutually exclusive investments. Let's start with our first definition. We say investment alternatives are independent when the selection of one does not restrict the selection of another. Let's look at our first example, which illustrates this definition. Here we have alternative A, which is to replace a gas-fired boiler with a more fuel-efficient unit. The motivation there being to save fuel cost. Alternative B is to replace the plant electrical control system with a smart system that would reduce the peak load from 450 to 350 kilowatts. The motivation there is to reduce the electric power bill because that's usually based on consumption and also on the peak load. Now, since the alternative A deals with fuel from a natural gas supply and B deals with electric power, there's very little relationship between these two in the technical sense. So for practical purposes, we could say that they're independent. Then we have the options, do nothing. We represent that by the symbol phi from the empty set concept in probability theory. Option A, which is to replace the gas-fired boiler. Option B, replace the plant electric control system. And then the combination A and B, which is to replace both. So we really have four options in this particular example. Let's go on to our next definition, which deals with mutually exclusive alternatives. This is where investment alternatives are such that if you select one, you cannot select any of the others, or the selection of one precludes the selection of another. So let's look at an example where this might apply. Here again, we have a situation of a boiler. In an alternative A, we're thinking about replacing a gas-fired boiler with a more fuel-efficient unit, specifically from manufacturer X. And then in alternative B, we're thinking about replacing that same old gas-fired boiler, but this time with a more fuel-efficient unit from manufacturer Y. Now, clearly, it wouldn't make sense to replace one old gas-fired boiler with two new ones. In most situations, that would be illogical. So we say that these two alternatives are mutually exclusive. So the options then are do nothing, replace the gas-fired boiler with one from manufacturer X, that's alternative A, or alternative B, replace the old unit with a new one from manufacturer Y. And the combination alternative, A plus B, in this example, doesn't exist. Let's continue with our definitions and talk about contingent alternatives. We say investment alternatives are contingent when the selection of one depends on the selection of another. So let's look at an example where this might apply. Let's think about installing a standby diesel generator for a refrigeration system where the capacity of the generator is 350 kilowatts. The motivation there is to provide power in case there's a storm that knocks out the power system, or in case the demand on the power system is so heavy that there's a brownout, which might damage your factory equipment. And let's think about alternative B, which is to install a smart electric control system that reduces the peak load from 450 to 350 kilowatts. Now let's think about these two alternatives. If you just get the generator that has a capacity of 350 and you have a power outage and your factory tends to run at a peak load of 450, the generator is not going to do the job. So you really need to install both if you're going to install the generator. So we say that A depends on B. That's an example where we have a contingent alternative. Alternative A is contingent on the installation of alternative B. So in this example, we have three options. We have the do-nothing alternative. Alternative B, we can go ahead and do that without worrying about getting a generator, because we should still be able to get a reduction in our power bill by reducing the peak load. But then we can also do A plus B, where we install the smart control system plus the generator for standby use. And there we get two benefits in the power bill. One is we get the reduction based on the reduced peak load from 450 to 350 kilowatts. And the other is we get a reduction because we now have an interruptible supply, and that can translate into a lot of money. In fact, there are power companies that are offering strong financial incentives for companies to install such standby generators. Let's go on with some more definitions. Let's talk about complementary alternatives. This is a situation where you have two or more alternatives where the combination is likely to be worth more than the sum of the individual worths. So let's look at an example in the field of logistics. Let's imagine that you have a company and you have a warehouse and you're thinking about gaining the distribution rights to distribute your products in Zone A. That's alternative A. Alternative B is for the same company to gain the rights to distribute products in Zone B, where Zone B is adjacent or very close to Zone A. So then it makes sense to consider the combination where you get the rights to obtain both A and B. You distribute your products in both zones, and normally you would expect some savings in transport costs, either because you're going to have more full truckloads or you're going to have better routes, shorter routes, better coordinated routes. You're going to get some savings by having both zones. So then we would consider these options. Of course, the do-nothing alternative, represented by the symbol phi. Alternative A, distribute only in Zone A. Alternative B, distribute only in Zone B. And then we would have to define a new alternative, C, which is the combination of distributing in both A and B, but reflecting some reduction in transport costs. So we say that then A and B are complementary because the combined worth of C would be greater than the sum of the worth of A and B. Of course, we can think in the other direction. We can think of competitive alternatives where the combination results in a relative worth that is less than the sum of the individual worths. This would be a situation where the projects are not mutually exclusive, but they're competitive in some sense. So let's look at example 5. We've got a gas-fired boiler again. We seem to have a predilection for examples with boilers and generators. We're thinking about a more fuel-efficient unit for alternative A. With alternative B, we're thinking about installing a system of sensors and closers, automatic sensors and closers at doors, windows, and other openings in the roof or in the sidewalls to reduce the heat loss during the winter season. Now, clearly, we can have a combination. We can implement both, but practically speaking, the savings are not additive. Because if we implement both, then the savings we would have estimated for only A would not be realized, and in the same way, the savings for only B would not be realized. So we would consider the do-nothing alternative, alternative phi, alternative A all by itself, B all by itself, and then we would have to define a new alternative C that's based on A and B, but reflecting some loss of the savings. Let's move on now to our numerical examples. In the first example, we're going to evaluate two alternatives, A and B. Alternative A has an investment of $300,000, a life of 4 years with a net cash flow of $115,000. Alternative B has an investment of $400,000. It runs for 5 years. The annual net cash flow is $125,000. Minimum attractive rate of return is 15. There's no budget constraint, and we're going to use present worth to make a decision. So let's look at alternative A. But first, let's line up the projects, the combinations. We've got phi, the do-nothing alternative, alternative A, B, and then the combination A plus B. The present worth of the do-nothing alternative is 0 by definition, because any money we put in the do-nothing alternative would then simply be reinvested at the minimum attractive rate of return. And any future cash inflows from that, when discounted back to time 0 at 15%, would be equivalent to the amount that we invest. So the present worth there is 0. For alternative A, it's a simple equation. The investment is $300,000. That's at time 0. The return is $115,000 per year. We take the series present worth factor at 15% for 4 years, and that gives us a result of $28,300 $323. That exceeds 0, so A, as an investment alternative all by itself, is acceptable. The analysis for B is similar. The investment is $400,000. The inflow is $125,000. That occurs for 5 years. We apply a series present worth factor, this time for 5 years. That results in a present worth of $19,019. Since that exceeds 0, project B is acceptable. And then we will evaluate the combination A plus B. That's very easy because the present worth of the combination is simply the sum of the present worth of the components in that combination. That, of course, is positive, a very large number, 47,342, compared to the other two numbers. So the combination is acceptable, and that's all we have to evaluate. We only had 4 options, including the do-nothing alternative. There's no budget constraints, so we pick the option that has the largest present worth. That's the combination alternative. Note that if we had mutually exclusive projects, we would select alternative A because it had the larger present worth. Its present worth was larger than that for B. And just as a reminder, to compute the present worth of a combination of 2 or more independent investment alternatives, simply add the present worth values of the individual investments. This makes present worth a very attractive criterion for combination alternatives. Now let's move on to our last example, example 7. Here we have 2 mutually exclusive alternatives, C and D. Mutually exclusive meaning we can pick either C or D. Of course, we have the option of picking neither one, but we cannot pick the combination. Here's the information for C, an investment of $200,000, project life is 6 years. D has an investment of $260,000, project life is 6 years. The annual net cash flow for C is $85,000, and for D, $125,000. Minimum attractive rate of return, 15%. Again, no budget constraint. And we want to use rate of return to make a decision. So we have to align up these projects in the right sequence. And the sequence is, of course, do nothing, C, which is the smaller project, and then D. There are no other projects to evaluate, so these are the only options. So we set up the present worth equation for C. We want to set this present worth at some unknown interest rate I and set that equal to 0. It's a series present worth factor for 6 time periods. When we set this expression equal to 0, we then get the result that the series present worth factor should be 2.35294. And then when we go looking for an interest rate that matches that, we find out that it's 35.7%. So we would either do that on our calculator using an iterative routine, or we might use a spreadsheet or a computer program, or we might go into the interest tables and use linear interpolation, perhaps between the 35% and the 40% table. Since this solving rate, the internal rate of return for C, exceeds the minimum attractive rate of return, we would accept project C for the time being. Then we look at the difference between the next project and the current defender. C is the current defender. D is now the challenger. The difference in investment is $60,000. The difference in the net annual inflows is $40,000. So then when we set up this present worth equation and set that equal to 0, we're looking for a series present worth factor for 6 time periods, and we want that series present worth factor to be equal to 1.5. It turns out that the solving rate is relatively high, 63%. That may be beyond the reach of the tables. Practically speaking, all we really would need to know is that it's somewhere above 50%. But if you have a calculator or some kind of calculation routine on a computer, then you could probably solve it at 63.1%. Since that exceeds the minimum attractive rate of return, we would accept D. We've run out of projects in our sequence. Our original sequence was phi, C, and D, so we stop. The final choice is D for mutually exclusive alternatives. And just as a note, if we had independent projects, then we would select both, because we could go ahead and compute the internal rate of return for D all by itself, and that's 42.3%. We would have, of course, suspected very strongly that it's above the minimum attractive rate of return based on the incremental analysis. So for independent projects, we would select both. For mutually exclusive projects, we follow the incremental procedure, look at C, that's acceptable, then look at D minus C, that's acceptable, so we make our final choice, alternative D. So let's summarize what we've done in this lecture. We have summarized some relationships. We've defined 5 different kinds of relationships, starting with independent, where the selection of one project doesn't affect the selection of another; mutually exclusive, where you can only select one project from a group; contingent, where you cannot select a particular project unless you select another one. One project depends on another one; complementary projects, where you gain some kind of synergistic benefit by having a combination alternative; and competitive projects, where you lose something when you combine 2 individual alternatives. And then we demonstrated 2 criteria. We demonstrated the present worth criterion with independent alternatives, and then we demonstrated the internal rate of return criterion for mutually exclusive alternatives.